All right, hello and welcome again. We're here with our crystalline silicon solar cells lecture series. We're going to be talking about our manufacturing, part 2. And here's our outline. We're going to go from sand to cell. We'll talk about first making wafers, then cleaning them, texturing, diffusion, screen printing, and firing. So it's going to be the process all the way from the sand on the ground to the solar cell. So again, here's our screen printed solar cells. The two on the left are mono, two on the right are poly. And how do they start? Well, they start as sand, really. And they get processed a bunch, and eventually we create a photovoltaic cell out of them. So here's the overview of the manufacturing sequence. You start with your sand, which is either silica or quartz. You clean it a bunch, and that'll produce metallurgical grade silicon, which is extremely pure, but it's still not pure enough for semiconductors. So it has to undergo a bunch more processing again to become semiconductor grade silicon, achieve that level of purity. Once you have that, you create ingots. So the ingots on the top are polycrystalline, the ingots on the bottom there are monocrystalline. Then you wafer them, so you cut them up, and then you do a bunch more processing, and you create a cell out of that. So how does it all start? Well, the feedstock is silicon oxide. So silicon doesn't exist in nature in a pure form. So you harvest it, you collect it from the ground as silica sand or quartz, and then you have to process it. So the first thing you do is you create metallurgical grade silicon out of it. So how do we do that? So we have silicon oxide. So we need to get rid of our O2. What do? We put it inside of an extremely hot furnace. We get it up to 1500 to 1200 degrees C using graphite electrodes, and we add a bunch of coal to that. So what does this produce? It produces silicon and carbon dioxide. So great, we separated the silicon from the carbon dioxide. It's about 98 to 99% silicon, and that sounds very pure, but again, that's not pure enough for semiconductor grade silicon. This is metallurgical grade silicon. So here's just a quick example of a metallurgical grade silicon processing plant. As you look at it, it's very hot, right? That's a lot of fire. It's quite a hot process. It's fairly complicated and takes quite a bit of energy. But here's a quick example of a plant. So what do people use metallurgical grade silicon, right? I said it isn't going to be used for semiconductors, although a little bit of it is used for semiconductors, a little bit of it is used for solar, because metallurgical grade silicon is quite a bit cheaper than semiconductor grade silicon. But it's largely used for steel and aluminum silicones and things like that. But to get to semiconductor grade silicon, we need to purify it even more. So now that we have our mostly silicon, we have a three-step process. The first thing we create is trichlorosilane, or TCS. Then we distill it, and then we reduce it to silicon. So it's kind of confusing. Why are we taking this mostly pure silicon and then adding contaminants to it? Well, we got to do one step backwards to go 2 steps forwards here. So first things first, we have our metallurgical grade silicon. We blow hydrogen chloride over it at 300 degrees C. This produces the TCS. Now this also creates a bunch of other gases and other contaminants, but TCS has a low boiling temperature, so we just boil those off using distillation. And then after that, we need to reduce it. And what do I mean by reduce? We have TCS, which is silicon and 3 hydrogens and a chlorine, and we separate those two. That's what I mean by distilling, or that's what I mean by reducing. So the most common method is the Siemens method. So let's talk about that. So what's the Siemens method? Siemens method, basically you feed your TCS into a reactor. You get it up to 1100 degrees C. You wait for a very long time, a couple hundred hours. The TCS reacts with hydrogen, and this results in silicon being deposited upon these silicon rods. So again, you're probably beginning to realize there's a lot of high temperature processing going on here, but that's what's necessary to create semiconductor grade silicon, which is extremely pure. And here's an example of a polysilicon plant. This is LDK Solar Company. It's based in China, and it obviously it looks huge, right? But this is for industry level production, so massive amounts. And then now what? Now we have pure silicon. Awesome, right? A lot of hard work, pure silicon. So what's next? So first we'll talk about what's next for polysilicon. So first, you get another kiln, basically a reactor, and you put your polysilicon in it. You get it extremely hot again, right? Another high temperature process. It melts down, and then you add your dopant. So you either boron or phosphorus, so to make a P-type or an N-type wafer, and then you cool it off, and you just have a big square of polysilicon. So what do you do if you want monocrystalline? So monocrystalline silicon is a little bit more complicated, right? It is a little more expensive. So again, you put it in a crucible, generally a quartz crucible. Both of these processes generally use a quartz crucible. You melt it down, same old, add your doping just like you do with polycrystalline. But instead of leaving it there, now you add a monocrystalline seed. So what is that? It's just a little piece of monocrystalline silicon. That's all that the seed is. And then you twist and you pull it out. And by doing that, you get this ingot. So if you see that big silver stick next to the person in the clean room suit on the slide, that's an ingot. That's what comes out. So it's this big, long, twisted monocrystalline structure. Obviously, it's going to cost more to do that than just heat up a vat of silicon and have polycrystalline. So now what? Now we have either a brick or a big, long ingot, and now we need to cut it. We need to wafer it. Generally, this is done by a wire saw. The wire saw is fairly expensive. The blade has some diamond particles in it, so it's pretty expensive. It cuts the wafers fairly well, but causes a good amount of different microfractures and things like that that'll have to be taken care of. But this is generally how it's done. It's just a wire saw grinding across it. So now that you have wafers, so that's what comes out after you cut them, you have wafers. Now you can run it through your manufacturing line. So this is a typical manufacturing line you're seeing here. So first things first is more cleaning and texturing. Then you diffuse phosphorus into it, right? That's our doping. Then you etch off a phosphosilicate glass, which we'll talk about. Then you have you deposit your anti-reflective coating. You print on your metal contacts. You fire it. You cool it, and then you characterize it at the end. So first things first, cleaning and texturing. So basically, what cleaning and texturing does is it gets rid of all the little microfractures and damage that caused by the wire saw. It gets off whatever's on the surface of the wafers. It just cleans it. Excuse me. And how does that happen? Well, you do a mixture of NaOH and KOH and IPA. And this etches silicon, and you heat it up to about 80 C, and you leave it in there, and that'll etch off the first couple layers of silicon. And also texture it, because remember, we want those little pyramids, so that way we have less reflection. Then what? Now we need to dope it. So what happens? We put the wafers inside of a tube, basically, and we run in nitrogen and oxygen over it, and then some of a thing called POCL, POCl3, and that begins to react, and you have a thing called phosphosilicate glass that forms on your wafer. So if you look at the bottom there, step 1, we run those 3 gases over. Step 2, we form a PSG. And then we heat the wafers way up at 1,000 to 1,200 degrees C, again, right, very hot. And this causes the phosphorus to diffuse into the silicon, creating a p-n junction. And then now you have that phosphosilicate glass that you got to get rid of, and that's fairly simple. It's just a hydrofluoric acid etch, and that gets rid of your PSG, and now you have a p-n junction on a silicon solar cell, or a silicon cell. It's not a solar cell yet. So here's a couple industry tools and lab tools for diffusion, as you see on the bottom there, and that's the wafers loading in. There's many different diffusion furnaces, but they all do the same thing. They diffuse some sort of dopant into a material. So next, now that we have diffused and we have a p-n junction and we have almost a solar cell, no metal contacts yet, but it will create electron hole pairs when light shines on it. Now we put on an anti-reflective coating, as we talked about before. So how does that work? Basically, you put your substrate into a chamber, you vacuum everything out, put it at a low pressure, and then you run SiH3, NH3, and N2 into the chamber. Those begin to react and form a plasma. Then the chamber heats up to 300 degrees, and you apply an electric field over it, and that forces this plasma to deposit onto the wafer, and that results in silicon nitride and leaves hydrogen. Hydrogen comes off this reaction. And that's how you get an anti-reflective coating on your solar cell. And obviously you want that, so that way your solar cell is less reflective and you can absorb more light. So the main way of doing it is a PECVD, plasma enhanced chemical vapor deposition, and these are a couple tools that do PECVD. There's obviously various different ways of doing PECVD, but all the same idea. Excuse me, where you apply a plasma using heat and electric fields. Excuse me. So if you look at this slide, basically the bottom is a wafer with anti-reflective coating. That's what the blue is from. And so if the wafer isn't blue yet, then it just hasn't had an anti-reflective coating on it. So the next step after we have an anti-reflective coating deposited, we screen print. So we need to get metal contacts onto this. So basically all that is, if you're familiar with printing shirts or screen printing or anything like that, same idea. You have a screen, which is a metal mesh, and those mesh has little holes in it, and the metal can only go through those holes, and then you put a paste down. So you have your screen, you put a line of paste down, and then you rub a squeegee across it, and that forces metal onto the wafer, and now you have your contacts printed onto the wafer, and they're wet and not dried yet. So then before we get into that, we'll talk about paste in a sec. But the thing to be concerned about is your metal paste will etch that anti-reflective coating on the front, and also it'll sit on the emitter. Now, if it gets too deep into the emitter and hits the base, you have a short, which is a big problem. So that's just one thing to be aware of the amount of metal paste, and to be aware that if my metal paste gets through my emitter, I'm going to have a short. So let's talk about the paste. So the paste, at least for the front, is silver, and there's a thing called a glass frit, and that exists to etch through the dielectric, which is the silicon nitride, the anti-reflective coating. And then there's some organic binders and some solvents to provide the correct consistency. Usually companies don't want people to know their glass frit exactly, because it's kind of a trade secret and an important discovery for that company. But it's usually a borosilicate glass with some lead. So also, if you're ever working with silver paste, remember it most often has some lead in it. And then the rear contacts are a little simpler. It's just an aluminum paste, similar idea. You just screen print it on the back. Now that you have contacts on there, you need to fire it. But remember, there's all that other stuff in the paste. There's that. Let's visit that again. There's our organic binders, our glass frit, and our solvents. Now, firing, you run it through. That burns all those things off, one. And then the other thing it does is it fires the metal into the silicon, so they're bound together. And how do you do that? Basically, another high temperature process. You heat it up to 800, 850 C. You run it through a belt furnace, and that'll burn the things off that need to be burned off, and fire the metal into the silicon. So that's your firing process, and once it comes out at the end of your belt furnace, you have a functioning photovoltaic cell, and that's all for today. Hopefully this was enjoyable for you, and hope to see you soon.